Hello, this is Lab 2, the magnetic field of a bar magnet. So to introduce this lab a little bit, our main aim was to experimentally calculate the magnetic field on and off axis for a bar magnet, and then we would compare this to a coded model of one. And so the main model we used was a glow script code for the bar magnet, and fundamental principles involved were magnetic fields and specifically magnetic dipoles like our bar magnet. And then our main result was we succeeded in calculating the dipole moment for the bar magnet from experimental results, and then our coded model outputted values similar to our experimental ones. So the most important concept to know is that a bar magnet functions like a magnetic dipole. Just like a dipole that has a negative and a positive charge side, a magnetic dipole, in this case a bar magnet, has a south and north pole. And so we have this equation for the magnetic field from a dipole, and we can get this from calculating stuff like the magnetic field from a charge coming in a loop of current. Um, but this equation can also be simplified for applications like on-axis or perpendicular axis observations. And so in these equations, you see the dipole moment, this mu, repeated over and over, and that is just the dipole moment, which is pointing from the south to north pole of this dipole bar magnet. So for our actual experiment, we were able to record the power of our bar magnet using an app on our phone which can track magnetic fields. So our first step was to align our phone with Earth's magnetic field, so that way our x-axis would be unaffected by the field since it would be following it on the y-axis. So then we varied where our magnet was and actually tracked out how strong it was, and we did this both on axis as you see in the top image and then eventually off axis as you see in the other image. And then some assumptions we made during this process was that we assumed that the sensor for the magnets was in that bottom left-hand corner of my phone, which we experimentally found it out to be. And then we also assumed that the phone was placed perfectly in line so the Earth's magnetic field didn't affect it. And then we assumed that there were no other magnetic interactions with nearby objects. And then also in my case, my magnet would point consistently south to north in the left direction. So with the results of our experiment in the top left, you can see for varying different distances, we had different strength magnetic fields coming from our bar magnet. So obviously the closer you get, the stronger it would be. And so by averaging a lot of these values, we could isolate the distance dependence for the bar magnet, which in this case I found to be negative 3.14, which is not far off at all of the equation one, which we know is r is to the negative third power. And so other than the distance dependence, we also know that our magnetic field will depend on the strength of our magnet, which would be the dipole moment. And so we can use the constant part of our results, that negative 15.31, and we can say that that is the natural log of all the constant parts of our equation. And then we can rearrange to find our dipole moment, which I found to be 1.12 amp meters squared. And then moving on to the second part of the experiment, we tried it for off-axis, and we kind of recorded the magnetic fields from that perspective. But those took a little bit more work because we had to try and cancel out the effects of the Earth's magnetic field. So for our coded model, the most important part was a function for the magnetic field from a magnetic dipole, which you can see in the top left. And that was based off of the equation I first showed in the PowerPoint for that. And then from this, we could basically call a bunch of observation locations and see what our magnetic field was. So first we did that for on-axis locations, and then perpendicular axis locations, and then finally an off-axis location. And so the distance I actually used for all these calculations was the same distance as part 2 of our experiment, where we put the phone at 45 degrees. That way we could compare our results. So this was the actual output of our code. I coded mine to have the dipole moment facing to the left. So you can see our on-axis magnetic fields will follow this dipole moment to the left, whereas the perpendicular magnetic fields are to the right, the opposite way, and in less magnitude than the on-axis magnetic fields. And then finally, our off-axis magnetic field has a magnitude that falls somewhere in the middle, and you can kind of see it's in the transition between the two directions of the other two magnetic fields. And our experimental off-axis was actually slightly stronger than our coded version, and this is likely due to us not being able to get out all the interference from the Earth's magnetic field. So for some additional questions, if we didn't have an axis which was unaffected by the Earth's magnetic field, it would have been a whole lot harder to find out just how strong our bar magnet actually was. But if we knew how much the magnitude of the Earth's magnetic field was at the point we were at, it would be able to find. It would just be a lot harder. And then if we had two magnets that were back to back in this experiment, I would expect that all of our measurements would just kind of double in magnitude, as a stack of two magnets would essentially function as one larger magnet that was twice as strong.